So far, you may have wanted to print a complex model like this propeller using FEM software. Whether you need to print a large number of layers in Abaqus, which requires writing complex subroutines in Python scripts, the process can be very time-consuming. If you're interested in learning how to print any geometry with any number of layers in Abaqus, I highly recommend watching this video. Hi, I'm Saman Hosseini. In this video, I'll show you the Gcode translation service, which is designed for the Additive Manufacturing plugin in Abaqus. First, I'll discuss the importance of using finite element software like Abaqus. Then, I'll introduce the AM plugin and explain the significance of using the Gcode translation service. Finally, I'll provide examples created with this product. Why do we need to simulate additive manufacturing, AM, and welding using finite element methods, FEM, tools? The first reason is to obtain residual stress data. By managing the residual stress from the production process in FEM, we can also address the anisotropic properties that develop. Additionally, FEM software is crucial in calculating the fatigue life of a product. Residual stress can have both positive and negative effects on fatigue life, influencing it in either direction. Another reason is for analyzing inherent strain. Simulation allows us to measure the dimensions of the melting pool. One benefit of this is that we can predict material state transformations, from powder to liquid and then to solid, during the Selective Laser Melting (SLM) process. This is crucial for assessing porosity before producing the part. Simulations also help us discover domains where phase transformations occur. For example, during welding, significant changes in material crystals at the micromechanics scale occur, especially during the transition from austenite to martensite. These transformations affect the material's strength and yield stress. By using simulations, we can observe the impact of these phase transformations. Now, in this slide, I will introduce the AM plugin. For instance, you can see the scan patterns labeled A and B. Generating these scan patterns through subroutines and Python scripting can be challenging and labor-intensive. Our goal with this plugin is to simplify the process, allowing you to generate these scan patterns with ease. So, if I were to introduce this plugin, as you can see, these are some of the working environments of the AM plugin. Initially, we have the event series, which includes the scan pattern and the path of material deposition. This illustrates the path of material deposition and the path of heat flux produced in the event series. Additionally, this section represents the material input, which indicates the amount of material to be added during the event series. We also have the moving heat source, which utilizes a double ellipsoid Goldak model. This can be applied without any coding, simply by adjusting the parameters. Additionally, there's the cooling module, where we can define convection and radiation interactions. An important point is that all the work performed with this plugin directly inputs into the INP file, which is then read and used by Abaqus software. In the previous slide, we introduced the AM plugin. As we observed, it allows us to generate the paths and event series for complex geometries, which can be time-consuming and challenging to code manually, such as through Python scripting. This task can be more easily accomplished in software like Cura, which allows us to print any shape using various techniques and quantities. For example, we can use a 3D printer to generate Gcode from a model in Cura. However, there's a problem. The Gcode generated by this software is not compatible with the AM plugin format, making it unusable within the AM plugin. So, what's the solution? The solution is to use our developed product, the Gcode translation service. I highly recommend using this service. With it, any Gcode you have can be converted into a format that is understandable and usable by the AM plugin. So, what happens if we want to export from Cura software to Abaqus directly? Unfortunately, Cura software cannot be exported to Abaqus directly. So, what are we going to do? First, we translate the Cura software Gcode and convert it into a format that can be used in Abaqus. At this stage, we can easily take any model we want and print it in Abaqus. Recently, the construction of customized implants has garnered significant attention, particularly with Selective Laser Melting (SLM). There is a substantial amount of ongoing work in this field. Here, you can see an example of a hip implant produced using the SLM method. With the code I have generated and the AM plugin, you can print any model, but it doesn't stop there. Having a solid and standardized background in building and manufacturing items in Abaqus is crucial. For those who consider themselves experts in this area, this knowledge will certainly shorten development time and ensure accurate results. For this reason, my email is provided below, and I invite you to contact me for coaching in this field. Another benefit of using this method and the Gcode translation service in conjunction with the AM plugin is that it allows for effective management of heat generation and calculation of residual stress. After completing the simulation and finishing the production process, the valve body you see here has been successfully produced. In this tutorial, I will show you examples of LPBF, laser powder bed fusion, and WAAM, wire arc additive manufacturing. I will also provide a practical example to help you understand how to use Gcode effectively. So, stay with me. At this stage, I want to start by opening the Cura software, which is a free tool you can use. After that, I will open one of the Cura projects that was previously set up. Here is a propeller model, and as you can see, a number of settings are required to print this model, such as the thickness of each layer. Keep in mind that this is a trial and tutorial model. I will show you how to print this model. The infill density percentage will affect the porosity. Here, we have different infill patterns available, such as zigzag, grid, and triangle, among others. You can choose any of them based on the work you are doing. We have about 14 different patterns that you can use. You can also define the speed here, but I've set it in a code. You can use this for controlling the slicing process. I will click on Preview now. Here, you can see the path of the heat source and material deposition nozzle. The key point to note is that the origin coordinate system we use in this software should be the same and compatible with the coordinate system in Abaqus because these codes are based on Cartesian coordinate systems. It's very important to use the same coordinates in Abaqus as we use in this software. Now, you can see that every layer is being printed in this way. Save the model as a Gcode file. Here is the file name. We can save any model we want in Gcode format. In fact, this file should be saved in Gcode format. For those purchasing this product, a link to access it on the website will be provided in the description. Here is the file we produced together, and we obtained the output from Cura software. I've located it here. Remember to use the Gcode format. I've uploaded it, and now, in the Gcode translation service environment, I will enter 1000 watts. Since this is in millimeters, the power must be set to 1000 watts. The layer thickness is also set to 0.3 millimeters. As you can see here, there are no units specified, just like in Abaqus. You must be careful about the units and ensure that the same values you entered in Abaqus are used here. For the number of layers to be deleted, I set it to 0 so that all layers are included. For the cooling time between layers, you can specify the cooling time as you wish, whether it's 10 seconds, 20 seconds, or 100 seconds. For example, I will enter 10 seconds. Additionally, for the speed of material deposition and heat source movement, I will enter 10 millimeters per second, and then I'll press Submit. Now, we just need to wait a few seconds for the files to be generated. Once ready, we can download the files from here and review them. As you can see, it's quite simple. The files were created for us without any effort or code writing. Now, 2 files have been generated. Let's open the files. In the same way, we observe the thickness of each layer, which is set to 0.3 of a millimeter. This is the material input. Here, we have the time, and these are the X, Y, and Z coordinates for the movement of the heat source generated in the event series. This is the power, and we also have the Z, X, and Y coordinates, along with the time associated with each step. You can see how straightforward it is, just a few clicks, and that's what was generated. I'll leave it as is. We took the Gcode and converted it into the event series format. which can be directly used in Abaqus. This is what we did with the Gcode. We converted it into a format that is usable within the Abaqus plugin. The first step in setting up the propeller welding model is to enter the 3D model into Abaqus. To do this, go to File and select Import Part, then choose the 3D model. Here, it is in step format, so click OK. I have already done this previously. Next, you need to create a material. This material should include properties such as conductivity, density, Young's modulus, since it is a thermomechanical model, thermal expansion, plasticity, and specific heat. After creating and using this material for the part, ensure that everything in the assembly is consistent. The X, Y, and Z coordinates must match between Cura and Abaqus to avoid any irregularities in the model. Pay close attention to this. Then, select and create a heat transfer step and perform thermal analysis. You can see the heat flux and thermal properties of the field output model. I have selected 1000 frames for thermal analysis here to avoid making the ODB file too large. I'm not applying anything in the interaction and load modules, as we can apply those settings directly through the plugin. I've set the element type to DC3D4, which is a tetrahedral element used for heat transfer analysis. Now, we need to make a copy of this model. By copying the model, I can rename it to mechanical. I've done this before, so this is now the mechanical model. In the mechanical model, we need to add the boundary conditions and create 3D stress elements. The heat in the mechanical model will also be based on the results from the previous thermal analysis. After completing these two steps, it's necessary to define a set for each of the thermal and mechanical steps. I've already done this. One set is for the thermal step, and another set is for the mechanical steps. Now, it's time to use the AM Modeler plugin. I've done this before, but to help you understand better, I will go through the plugin setup again so that you can follow along. I set the analysis type to thermomechanical. For the process type, I selected laser direct energy deposition for the welding case. The thermomechanical steps are automatically selected here. I click OK. In the Event Series section, I click on Power Magnitude. I use the CSV files that we created together with the code. Here, I will input the heat source movement data. As mentioned, one column is for time, one column is for X, one column is for Y, one column is for Z, and one column is for the power of the heat flux. I click OK. Additionally, one more path is needed for material deposition. Here, I will select the material deposition file. The Gcode we generated for the material includes the timing for the X, Y, and Z coordinates. The two files we generated are similar, but in this case, instead of specifying power, we define the material deposition status for the nozzle. The first path is for the thermal source, and the second path is for the position of the nozzle that deposits the material wire. Simulating thermal and mechanical models, especially with a large number of layers, is very time-consuming and requires significant runtime. Therefore, it's a good idea to check the path before executing the full simulation. By reviewing the path and event series, we can ensure that everything is correct and exactly what we want. To do this, click on the event series and select Plot. As you can see, this is our model, and this is the path that has been defined. The path and the model match exactly what we created in Cura software. However, there are some extra lines between these lines, which is due to the difference between the logic of the Gcode and the logic of the plugin. The difference between the logic of the Gcode and the logic of the plugin is why you see some extra lines between the intended paths. This doesn't mean that the new material won't be added correctly. Most of the lines are accurate and correct. Now, let's review the material setup. For the event series, the second event series was automatically selected. Here, I set the deposition processor to bead. The sets we created earlier have been automatically chosen because they were previously defined. I set the activation type to full and configured the stack direction for the structure to be added along the Z-axis. The material addition direction is set to Z, indicating the level of material that can be added to each layer. The height of material deposition is set to approximately 0.35 mm to ensure complete coverage, with the material bead width set to 1 mm and the activation offset set to 1 mm. The deposition process has two methods, below and above. I chose the below method, which is appropriate for this setup. After completing the material input module, I proceed to the moving heat source section. This is associated with Event Series 1, which includes the heat flux. I selected this option accordingly. The energy distribution can be configured in various ways. For example, if I want to use the double ellipsoid Goldak heat flux profile, I access the settings and input the Goldak parameters. Additionally, I set the box size factor to 1. As you can see, we did this without writing any code. We defined the Goldak heat flux parameters. I then set the absorption coefficient to 0.7. Click OK. Now, let's move to the cooling module. If you recall, we did not define the cooling interaction in the thermal model. So, here I set the film coefficient to 0.025. The sink temperature to 25 degrees Celsius, the radiation emissivity to 0.4, and the ambient temperature to 25 degrees Celsius. After setting these parameters, we execute them in the cooling plugin module. Well, in the thermal module, there's nothing more to cover except the mechanical part. Remember, once the thermal module is completed, you can use the predefined field option to transfer the thermal results and apply them in your mechanical module. Now that everything is fully set up, let's move to the results module and review the results together. First, let's examine the thermal model results. Viewing the simulation frame by frame can significantly increase the ODB file size. To manage this, I set the number of frames to 1000, and the result was satisfactory. Regarding porosity, some elements may be missing due to the infill density being set to 40%. Increasing the density reduces the number of missing elements. Next, let's review the mechanical model results. Here, you can observe the residual stress generated by the welding process. Additionally, the model displayed has a higher infill density compared to the previous model. Here's an example of printing a box using the laser powder bed fusion method. This process is trajectory-based powder bed fabrication. At the beginning, a layer of powder is applied, and then the heat source moves according to the specified pattern, causing the powder to melt and subsequently solidify upon cooling. The infill density is crucial here, as it directly affects the final porosity. For subsequent layers, the process repeats. A layer of powder is applied, followed by the heat source moving according to the specified pattern. The material transitions from powder to liquid and then solidifies accordingly. Regions that experience phase transformation are depicted in red, while regions where the powder did not melt remain blue. These simulations help us assess the porosity of samples produced through additive manufacturing. Our website is dedicated to providing high-quality tools and resources to support researchers and students. Your feedback is invaluable to us, and we encourage you to share which products and codes would be most beneficial for you. I'll be reviewing your comments to help prioritize the development of content that meets your needs, along with guiding you through additive manufacturing and welding techniques from start to finish. I'm also deeply involved in both academic and industrial projects. If you have any questions or insights about 3D printing and Abaqus, please feel free to reach out. Thank you for watching, and I look forward to seeing you in the next video.
Let's introduce Saman Hosseini, a member of the Hyperlyceum team. Saman, a PhD student, brings over 6 years of extensive experience in Abaqus with more than 400 successfully completed projects, including fracture mechanics, composites, additive manufacturing, biomechanics, and beyond. He leverages advanced simulation solutions coupled with Python scripting and Fortran subroutines. Saman offers free online consultation sessions tailored to graduate students, professors, and industry experts seeking to learn modeling techniques. With over 200 hours of tutorials and having mentored over 100 students, he is dedicated to helping you with your research, education, and industry-related projects. Contact Saman today to schedule your free consultation, discuss your project, and confidently tackle its challenges.